Today's lesson, rational functions, and this is the biggest, baddest lesson so far. And by baddest, I don't mean that each individual detail is so difficult. It's not. Each individual detail, I hope I can explain in such a way that the individual details will be reasonably clear. It's just that there's so many details, and that's why the note, I really suggest you print out a blank version of the note, get it all ready to go, and copy this out as you go. Pause when you need to, because you really need to take in these details carefully and sort of know where they are in the video and in the note, so you can go back later and go over the details again. Because the first time through it, the idea that you could absorb all the details is pretty unlikely, because there's just so much that's going to come at you. One thing that's going to come out of this, though, is the beauty of the math we've done so far. Sometimes it's lost in grade 9, 10, and 11, the beauty of what we're coming up with here. And it all comes together here in this lesson. That's the first really, really good prelude to calculus and the analysis powers we're going to have. From now until the end of this video, probably an hour or so from now, the analysis powers you're going to gain from this, it's really quite surprising, the ability to look at a function and really tear apart what's happening with it, and very complicated functions. Also, a lot of the skills that you've been using through grade 9 to 11 that might have seemed like useless skills will now be invaluable, and so you'll start to see the big picture here. We start by defining rational functions. Simply put, a rational function is a fraction with a polynomial in the numerator and another polynomial in the denominator. That immediately means that all the skills that we developed the last two chapters for factoring and solving will be used here, because it's going to be a polynomial we're talking about in the numerator and then another polynomial in the denominator. So here it is in the red box, the formal definition from a textbook. A rational function has the form h at x equals f at x over g at x, where f at x and g at x are polynomials. All we're saying is the functions we're going to look at today, there's going to be a polynomial in the numerator and one in the denominator. Then it says some important things here that we better take a look at. I'll get into my yellow highlighter here. The domain of a rational function consists of all real numbers except the zeros in the denominator. In grade 11, you called these restrictions. Now they'll be called domain issues, and we'll finally get to the bottom of why they were so important. In grade 11, it just seemed like something you had to state at the end, comma, x can't equal 2, big deal. Now we'll look at what the big deal is, because it's going to take on a whole new meaning here. And the second line says the zeros of h at x are the zeros of f at x. And what that's trying to imply is that if you want the zeros of this rational function h at x, all you need is the zeros of the numerator. And I'll show that in the examples here. So this is a good box to look at before we start. It's also a good box to look at after I'm done. Well, I'm going to jump right in and start doing some examples. This says, find the domain and the intercepts of this function. And you can actually do these things. You have the weapons to do these things. You may not know it yet. You got to see it in action. And let's talk about domain, first of all, because that's what it asked for first. Domain, the one thing we know about domain for rational functions is that we cannot divide by 0. This was called restrictions last year. So what we know is that x plus 2 can't equal 0. And if I move that 2 over, I get x can't equal negative 2. And up until now, that was just a statement we made. We go, okay, x can't equal negative 2. No big deal. And I'm going to jump ahead. What I've done in this presentation is later on, I've got a computer to produce the graphs. And not till the very end of the lesson, the last two examples in the whole lesson, do I expect that you'd be able to produce those graphs yourself. No. What I did is I put the graphs up, and I'm going to bring one up in a second, and you can see what that domain issue, how it manifests itself in the graph. And all I want you to get from that is, oh, that's how x can't equal negative 2. Not look at the graph and say, oh, I could graph that whole thing. Just see this domain issue. So when I scroll up, here's the graph that we're talking about. I'll label it, this is the A graph. And if you look at the graph, can you see that x can't equal negative 2? Now, it works both ways. The algebra says x can't equal negative 2, so the graph cannot go through negative 2. But the other side of it is this graph doesn't equal negative 2, and that's why there's the denominator there of x plus 2, because that means x can't equal negative 2. It works both ways. They're interconnected, the graph and the algebra. Okay, so don't worry about the rest of the graph right now. just look at this thing and say, oh, look, x can't equal -2, and I'm going to give something away here. That's called a vertical asymptote, which you may have seen before. You may have seen that word used before, and it's an imaginary line. People say it's an imaginary line. I don't know if it's imaginary. It's there. There's a line there. It's not part of the graph, but it's this line that this graph cannot go through. And that's what a restriction is a domain issue, like you're seeing there. Back to here. We found the domain of the issues of this. The domain x can't equal -2. And I didn't use all the fancy word symbology of domain there. I just said, hey, x can't equal -2. The other thing you can do, what you might not realize you can do, is you can find x-intercepts. And just like all the other grades, starting grade 9, if you want to find the x-intercepts, you set y equal to 0. That's always been true. So here I go 0 equals 7 over x plus 2. Now I've got a rational expression on the right-hand side that I've got to deal with. And the easiest way to deal with this is to say, listen, I want to get rid of dividing by x plus 2. The opposite of dividing by x plus 2 is multiplying by x plus 2. And so I move the x plus 2 over to this side. But waiting there is a 0. So 0 times x plus 2 is 0. And I get 0 equals 7. Now, don't let that blow your brain up just yet. We'll let your brain blow up on that in a second. But what I want you to notice is that to find the x-intercept of this function f at x, all I did was actually take this numerator and set it equal to 0. I'll show those steps every time, but there's a massive shortcut there that's mentioned up here. If you want to know the zeros of a rational function, what you want to know is the zeros of the numerator. Now, back to this 0 equals 7 nonsense. When does 0 equal 7? What you're asking the math in this situation is, what will it take for me to get an x-intercept? And what it'll take to get an x-intercept is that this function will come out to 0. So, to come out to 0, that means the numerator has to come out to 0. So to come out to 0, we need 7 to come out to 0. And can 7 come out to 0? No. 7 can't come out to 0. There's no solutions here. Don't let that freak you out. Let's go take a look at the graph to see what that means. Take a look at the x-intercepts of this graph, which, again, I wouldn't ask you to produce at this point. I just want you to see how it manifests itself here. Look at the x-intercepts. Well, there isn't any. So when you try and do the algebra to solve for an x-intercept that doesn't exist for that function, you're going to get nonsense at some point, an equation that is nonsense. And here, the nonsense is 0 equals 7. So don't let that kind of stuff to freak you out. It's a little bit like, not exactly like, back in grade 10 and 11 when we got square root of a negative. The square root of a negative said, no, you don't get any real answers out of this. In this particular case, there's no way out of this thing. There's no solutions to this thing. The other thing we want is y-intercepts. And to get y-intercepts, we set x equals 0. That's a little easier. Y equals 7 over 0 plus 2. So I get y equals 7/2. For the purposes of graphing, I probably want just the decimal so I can graph it. Y equals 3.5. And when we go to the graph, that's a little easier to see what happens here. You can see that y-intercept at 3.5 there. Okay, again, could we do all the graphing at this point? No. We got lots of other things to talk about what it would take to graph this thing. I just wanted you to see those two features, that right now, with the math knowledge you have, we can analyze the domain of things, and we can find the x and y intercepts. Is that helpful? Yeah, it really is helpful in the big picture, and you're going to see when I get to the final two examples of this lesson that it's going to be important information. We'll get to all that. For now, domain, x and y intercepts. So important that I'm going to do it on two other examples. I'm going to go through the same procedure again. So here, B, domain. X squared minus 3x minus 4. We don't want that to be equal to 0. Some people might have factored this before they took it out. You don't need to. I'm going to go, okay, x plus 1. X minus 4 can't equal 0. Therefore, x can't equal -1, and x can't equal 4. Again, last year, that would have been restrictions. You would have said, oh, x can't equal these two things, big deal. But when I look at the graph, watch what happens. The graph, there's this vertical asymptote at -1. and there's this vertical asymptote at x equals 4. The graph can't go through those values. It gets really close to it, and in my graph, and the way the resolutions come out there, it may look like it even gets to 4, but it doesn't. It nudges up against it, but never really crosses it. Again, I don't expect you to be able to produce these graphs at this point. I just want you to see how it plays out. The fact that those domain issues exist mean that in the graph, those x values are not possible. Oh, I want to label that graph too. That's graph B, so if later on I don't want to get confused between the graphs. Okay, what else was I supposed to do here? Oh, x-intercept. So for x-intercept, I set y equal to 0. So I go 0 equals x over x squared minus 3x minus 4. And this is going to happen every time with x-intercepts, is we're dividing by x squared minus 3x minus 4. Whatever that denominator is, it's going to come over and multiply by 0. And anything multiplied by 0 is 0. And so really, you can skip that step. And that's what that box up there was trying to say, is if you want to find the zeros of a rational function, just find the zeros of the numerator is what we're finding there. And the numerator here was x. So after some algebraic manipulation, I find out that x equals 0, which is just the numerator. Let's look at the graph and see how an x-intercept of 0 played out. In that graph, I had an x-intercept of 0 right there. Is that helpful? Extremely. Does it tell the whole picture? No, there's lots more to teach you before we can do the whole picture. And then for y-intercepts, set x equal to 0, so I get y equals 0 over 0 squared minus 3 times 0 minus 4. I get y equals 0. No new information there, but there could be new information there. This example just didn't happen to have any new information. That x-intercept of 0 is also a y-intercept of 0. No kidding. Okay, third example here. First, domain issues. X squared minus 4 can't equal 0. Factor that thing. X can't equal negative 2, or x can't equal 2. Go back to the graph, and you see that graph for C had vertical asymptotes at negative 2 and 2. Very easy to jump to the conclusion that any domain issues are vertical asymptotes, and that's not true. It really seems true because that's the only thing you've seen so far. But I want to keep your mind open at this point, is that when we have domain issues like this, they're very likely vertical asymptotes. And I'll show other examples before this lesson is out of how they would not be vertical asymptotes. So we'll get to that. But for now, we'll go, okay, domain issues seem like they're going to be vertical asymptotes because they often are. Next, x-intercept. Set y equals 0, so I get 0 equals 2x squared plus x minus 3 over x squared minus 4. Bring that x squared minus 4 over, and I give you permission to completely skip those two steps and jump right to here. That the x-intercepts of that function are going to be when the numerator equals to 0. You might run into the quadratic formula here. When this happens, this particular one doesn't. This thing does factor, but I'm not saying you won't run into that. So do a little thinking here, and I go, okay, well, 2x squared is going to be 2x and x. And so to get a positive 1x over there, I'm going to need a plus 3 and a minus 1. So what I get here is x equals negative 3 halves, or x equals 1. 2 x-intercepts there, negative 3 halves and 1. And if I go to my graph that I got the computer to produce, there they are, negative 3 halves and positive 1 on the graph. You can see how some of the information would be helpful here. If I just had the purple information you're seeing there, that would be enough to sort of get an idea what the graph might look like. But again, there'd be a lot of features missing, so we got to work away at that. And then for y-intercept, set x equals 0, so I get y equals, let's see, 2 times 0 squared, that's 0, plus 0, that's 0. I get negative 3 on the top. And then 0 squared minus 4 on the bottom, I get negative 4. I can simplify that to positive 3/4, which if I want to graph it, maybe I want to know the decimal value, 0.75, and that comes out in the graph right about there. So you can see actually the purple dots here sort of really indicate maybe that middle part, I'd have a good idea what was happening just with the vertical asymptotes and those 3 points. I'd go, oh, I sort of see what's happening here, but maybe not the whole picture, so we'll get to all that. Okay, so those 3 examples are supposed to highlight that you do have some algebraic powers here, and a lot of this stuff you could actually do with what you have already. You already knew how to do domain issues. You called them restrictions. You already knew how to do x and y intercepts, and a little bit different algebra here, but not this algebra doesn't get out of hand. Okay. Notice, though, some features that came out of this. And you might have seen this in grade 11, is there seemed to be sort of a horizontal asymptote here as well. Is that this one was heading out to y equals 0 on either side. That would be helpful to know if things had a horizontal asymptote. Because this one also has that horizontal asymptote at y equals 0. It approaches y equals 0 at the ends there. But this one doesn't do that. It approaches y equals 2. That's very strange. How could that possibly happen? And so we got to talk about that. We got to talk about horizontal asymptotes. And we do want to talk about vertical asymptotes a little bit more. These vertical lines I drew on here, these imaginary lines that the graph is attracted to, it heads towards them. So a little bit more conversation about that because those 2 things are going to help a lot in doing our graphs. So we move on to vertical and horizontal asymptotes. A little talk about these vertical and horizontal asymptotes we've seen. So the above graphs all had vertical asymptotes when there was a hole in the domain. I want to change that word hole because I got to use it for something else later, okay? The above graphs all had vertical asymptotes when there was a problem in the domain. An asymptote is a line that a graph approaches but never reaches. In other words, the graphs are really big or really small as they approach that problem in the domain. So more technically, out of a textbook here, vertical asymptotes. A vertical asymptote occurs when the value of a function increases or decreases without bound. Right here, this thing goes to infinity, heading to infinity. This the way, and that's what they mean by increases without bound. As the value of x approaches a from the left or right. So you see, as it was approaching 2 from the right, it was heading off to infinity. And it was heading 2 from the left, it was heading to negative infinity here. So it's heading off without bound as it approaches 2 from the right or from the left. In symbols, f at x goes to infinity, or f at x goes to negative infinity as x approaches a from the positive, or as x approaches a from the negative. I said that in the reverse order. So what we mean by that is, in this particular graph here, as x approaches 2, and we use this little symbol, this little positive up here in the superscript, as x approaches 2 from the positive side, the function goes to positive infinity. And as x goes to 2 from the negative side, f at x goes to negative infinity. Really stare at that for a second to make sure that's perfectly clear. Those are some handy symbols to talk about what these graphs are doing. How will you know if it's going to positive or negative infinity? You could sub in numbers. Actually, if you're stuck, you could. I could sub in 2.01 to the function or 1.99 to the function and find out that way. So if you're really stuck, just subbing in a number close there will do it. Seems sort of pedestrian, but we'll come up with some other methods, but that's always there for you. An horizontal asymptote is sort of the same idea, but horizontally. So a horizontal asymptote occurs when the value of a function approaches the number L as x increases without bound. So x is getting bigger and bigger, but now it's approaching some asymptote here. And it can approach it from above or from below on one side, or from above on both sides. There's lots of options of how this can play out, and you're like, how am I supposed to know? Well, don't worry about that right now. Just worry about that these things can happen. Now, notice also that horizontal asymptotes, a graph can go through it. So a horizontal asymptote isn't a domain issue. It's an end behavior. So we talked about end behaviors heading off to infinity on either side. This isn't heading off to infinity on either side. It's heading off to L. In the previous examples, we said it was heading to 0 or was heading to 2. So it's not a stop sign, not like a vertical asymptote. You can pass through a horizontal asymptote. You're just, at the end, you have to approach the horizontal asymptote, okay? So different definitions. That's why I said up here sort of the same, because you can go through a horizontal asymptote. This is one big problem that has caused people over the years right here. So I just want to highlight that, and I encourage you to highlight that, is that you can, if it happens, Don't let it freak you out. You can pass through horizontal asymptotes. They are not domain issues. They are not stop signs. They're just end behavior. So we already know how to find vertical asymptotes. Those are the domain issues. I warned you, there won't always be a vertical asymptote, but don't worry, I'll explain that by the end of the lesson. So for now, we think we know how to find our vertical asymptotes, but horizontal ones, the idea is we want to see what the function does for very large positive and very large negative x values. We're just talking about end behavior here. So really, please add this to your note. This is another end behavior. We've been talking about end behaviors, and it might have seemed like we covered everything. All the end behaviors. Those holding my arms up in either direction and going little disco moves, like heading off to infinity this way and negative infinity that way, those type of things. And it was just had to do with odd and even powers and positive and negative leading coefficients. Hopefully we beat that to death. Here's a new kind of end behavior, which is horizontal asymptotes. So what we want to find out is, what does a function do for very large positive and very large negative x values? That's what horizontal asymptotes are all about. And yes, I went with red highlighter there again. It's a big deal. Now, I want to go after a single function here, and I don't expect you to sub all these numbers in. I've got them all ready to go here so I can fill them in. If you're doubting me, you can sub a few of them in to see that I did a good job. And I'm going to do this function here. G at x equals x plus 3 over x squared minus 4. And I'm just going to do one example and walk all the way through it. And hopefully, I want to show you what's coming here, is hopefully the discussion I'm going to have with building these tables is going to lead us to some rules here. Hopefully, I'll say just the right things where these rules will make sense. And then I'm going to take a whole bunch of time and do some other examples. So let's talk about as x goes to infinity. That's what we really want to talk about, is as the function gets very large, as the x values get very large, what's this function going to do? Is it going to go off to infinity, like we've seen polynomials do? Is it going to settle into 0, like we saw in those first two examples? Is it going to settle into 2? Okay, so let me just sub in some numbers. So I sub in 100 into this function. On the top, it looks like I'll get 103, and the bottom I'll get like a million minus 4, like 996,000. Anyways, when I do all that and punch it into my calculator, what I get is 0.010304. And the reason that's so small is because even though I was subbing in x equals 100 into the numerator, that 100 got squared in the denominator, and the denominator was much bigger than the numerator. And if you go to a bigger number like 500, the top gets even bigger. It's now 503, but the bottom's like 500 squared, which is like 500 squared, 250,000. The bottom is getting so big so fast that this value of this function now is 0.002012. It's even smaller than it was before. And if I sub in x equals 1,000, the same thing happens again. The top has got really big. It's now 1,000, but the bottom's become like 1,000,000. So the bottom, the denominator is taking off so fast, it's just killing the numerator. And I'll fill in these other values. As the x value got bigger and bigger, this function value just keeps getting smaller and smaller because the denominator is getting big so unbelievably fast. And I'm going to bring in a new word here. Well, it's not all that new of a word, but a new word for this example is degree. Because the degree of the denominator was bigger, it grew so unbelievably fast that it got so much bigger than the numerator. When we did the division, we get these really small numbers, and now I get 0.0001, and then 0.341, and then 0.12345. And this sort of explains horizontal asymptotes in a nutshell. You see, it's getting closer and closer to 0. It's never going to get to 0, but it's going to get so unbelievably close that it may as well be 0. On the other side, the same thing happens, because all that's going to change is maybe the sign of the situation. The numerator is going to be a big number because I'm subbing in big numbers, but the denominator is going to be so much bigger because of the higher degree. So the degree is the key thing here. And when I type these in right off the hop, even with a number like 100, I can see what's about to happen here is that the value of the function has got incredibly small because the denominator is killing the numerator. And then I get some other values here. By the time I get up to 500, it's got smaller again. By the time I get to 1,000, it's smaller again, but negative this time. And we got to talk about whether it's going to be positive or negative. And there's some things to talk about how we're going to know it's going to be positive or negative. And I got to tell you, by the end, we're going to have all sorts of ways to know if it's positive or negative. And these values just keep getting smaller and smaller and smaller. And we're not going to build these tables. We're just not going to build these tables. We're hopefully going to be way better than that, where we know what would happen if we subbed in these big numbers. The degree of the numerator and the denominator is going to tell us what's going to happen here as we sub in these bigger and bigger numbers. And we've already got one of our degree rules already. Here's the general rules. Other than using a table of values, which we don't want to do every time. We did it once to learn. Other than using a table of values for large positive and large negative values, the horizontal asymptote can also be found by comparing the degrees of the numerator and the denominator of a rational function. Given that the numerator and denominator are polynomials of degree n and m respectively, so what I mean is we're talking about the degree of the numerator, we're going to just call n, and the degree of the denominator we're going to call m. And so the one we just found is when the n, the degree of the numerator, is less than the degree of the denominator. That's what we found here. This was a degree 1 over a degree 2. Then the horizontal asymptote will be y equals 0. Ooh, let's go back. Let's check those ones from before. A. Degree of the top was 0. Degree of the bottom was 1. And so I got a horizontal asymptote y equals 0 on the graph. There it is. Second example, degree in the top was 1. Degree in the bottom was 2. So the degree in the bottom was bigger. And again, I got that horizontal asymptote at y equals 0. Hopefully you're getting excited now, because a lot of these features of this graphs start to become possible for us to predict using just this little set of rules we got here. Okay, next. I'm going to jump ahead to the last rule here, is if, let's say, the n was greater than m, if the numerator degree is higher. Well, what happens if the degree was higher in the numerator is that instead of the numerator being much smaller than the denominator, it's going to be much bigger than the denominator. And what happens is the function goes off to infinity. And we'll do something similar to what polynomials did, that disco dance, off to infinity in either direction. It's not going to settle into some value. So we don't have a horizontal asymptote. Ooh, where is it? There is no horizontal asymptote when that happens, so we don't have to worry about a horizontal asymptote. How will we know what it's doing then? Well, actually, we can go back to our old degree rules when that happens. We can look at what the difference is between the degrees and work from there. A little bit more on that later. But for now, under the heading of horizontal asymptote, if the degree in the numerator is higher, we don't have to worry about a horizontal asymptote. This leaves only one case. What if the degrees are equal? Well, let's just imagine that for a second. I'm just going to draw a little function over here and say, okay, what if I had a function that was like 4x squared plus 5x, and then on the bottom it was 2x squared minus 9x plus 1. What would happen as I sub in big values? And I'll just sub in one big value to get a feel of what's going to happen here. Let's say I subbed in 1,000 into the numerator and 1,000 into the denominator. What you'd get in the top would be around 4 million. 4 times 1,000 squared. There'd be some other pieces there. There's an extra 5,000 there. And the bottom would have like around 2 million. So we'd have sort of, all that would really matter would be, we just have this 4x squared and this 2x squared. That's all that would be left. And so the x squareds would cancel, and I'd get y equals 2 as a horizontal asymptote. So for big x values, all we care about is the highest degree. We saw that before in polynomials, and the highest degrees are equal, but they would cancel. 4x squared over 2x squared, you get y equals 2. Let's go back to that one from before, because I tried to set it up similar to that one. Take a look at the one from before. 2x squared over x squared. For big x values, say 1,000. 1,000 is a great one to think about. On the top, I'd get around 2 million. On the bottom, I get around 1 million. And 2 million over 1 million is around 2. And that's what you saw here as this horizontal asymptote settling into y equals 2. I'm just going to label that on there. Okay. These rules will handle most situations. I just want to do a couple examples to really make it clear. Oh, use the general rules above, determine the horizontal asymptote for, what was the one that we did up here? X plus 3 over x squared minus 4. And what we'll say is, okay, that means the horizontal asymptote, who I've already used, jumping to the short form here, HA for horizontal asymptote. The horizontal asymptote will be, let's see, the degree in the top is lower than the degree in the bottom, So that means horizontal asymptote y equals 0. Is that what we found in our table? Well, yeah, it was heading to 0 on both sides. So yes. If you're worried about the positive negative part, how are we going to know the positive and negative? Don't worry about that just yet. We'll put all the pieces of the puzzle together in a little bit. Some extra examples. You might need a separate sheet of paper. Maybe there wasn't enough room in your note. Just 3 quick examples. So say we had y equals 3x cubed plus 2x squared minus 5 over 2x squared minus 4x plus 1. We'd look and we go, oh, degree on the top is higher than the degree on the bottom. We'd have our rules memorized, and we'd go horizontal asymptote. We'd say none. We wouldn't have to worry about a horizontal asymptote. What would we do about end behavior? Well, it's x cubed over x squared, so this thing would have the same end behavior as a degree 1 function. So you can actually handle it that way. We don't have to do a lot of thinking like that, but just so you know, there is ways to handle that, and you go back to your old thinking, which is all those disco moves we were doing from before. Another example, y equals 2x to the power 4 plus 5x cubed minus 4x over 4x to the power 4 minus 3x squared plus 5, and I'm just making up random stuff there. This is, you go back to your rules and you go, okay, the degrees of the top and the bottom were both 4, the degrees were equal, so for very large x values, what I would get is essentially y equals 2 over 4, the ratio of those leading coefficients, and so you get y equals 1/2. Let me go back to here and fill that in. If n equals m, then the horizontal asymptote is y equal ratio of leading coefficients. So that's what we do there, is we use the leading coefficients here. Here it was 2 and 4. That were the leading coefficients, and that tells me what my horizontal asymptote would be. And one last one, y equals 5x cubed minus 2x squared plus 7x plus 1 over 3x to the power 4 minus 5x plus 8, something like that. And we look and we go, okay, the degree of the denominator is the bigger one, so the horizontal asymptote will be y equals 0. The denominator will just kill off the numerator, and you think, oh, well, that's cubed on the top. It doesn't matter. The degree on the bottom is bigger. It will get bigger much faster for big x values, and it will kill it off, and it'll head to y equals 0. Now, as if that wasn't enough details in one lesson, there's one more type of asymptote to consider. Well, that's not true. There are other types of asymptotes, but there's one more type of asymptote to consider in grade 12. The reason we discuss it separately is it is a very special case. In the middle of this end behavior discussion, we started with end behavior being heading to infinity or heading to negative infinity, and now we've learned it can head to a horizontal asymptote. So really quickly, we've learned that it can head to a horizontal asymptote, that the function can approach some kind of horizontal asymptote somehow. But there's no reason that the asymptote has to be horizontal, and what we're going to look is at oblique asymptotes, where the function could approach some oblique asymptote. And here, actually, we're going to talk about linear oblique asymptotes, where it's approaching a straight line and moving forward. They don't have to be straight lines. They could be other shapes. But for now, we'll stick to linear ones, that it's approaching some straight line. But instead of the whole line being horizontal, it can be at an oblique angle. So an oblique asymptote, when does it happen? It's the result when the degree of the numerator is 1 more than the degree of the denominator. You can totally just memorize that. A lot of people do. Just memorize that you get a linear oblique asymptote. Whoa, another word needed there. Just want to be careful. A linear oblique asymptote is the result when the degree of the numerator is 1 more than the degree of the denominator. Again, you can memorize that. But to make it clear why that's true, if you're wondering why that's true, why it has to be 1 more, take a look at this simple example. Consider the function y equals 2x cubed minus x squared plus 3 over x squared. This fits the condition we just talked about. Degree on the top, 3. Degree on the bottom, 2. The numerator is exactly 1 more than the denominator. To understand its end behavior, we're actually going to divide it. I take 2x cubed minus x squared plus 3, and I divide each term by x squared. And when I divide 2x cubed by x squared, I get 2x. When I divide negative x squared by x squared, the x squareds cancel, and I get negative 1. And then when I divide 3 by x squared, I get 3 over x squared. Now, before looking on, just take a look at this for a second. I've wrote that function in a new form, and that form is very instructive. And a very powerful way to handle this situation is to divide it up. It has a lot to do with the quotient remainder dividend stuff that we were doing last chapter. And the optional way to write the answers, which we didn't get too excited about, but it's very helpful here. What I end up with here is a function that if I sub in a big x value, I can tell what's about to happen. For a large x value, I'm going to have 2x minus 1, and then we have this 3 over x squared term. And for a very large x value, this is not going to matter. It's going to be a very, very tiny little piece. So for a very large x value, this function really looks like y equals 2x minus 1. And y equals 2x minus 1 is a line. Boy, that's a lot coming at you in a short period of time. That is the kind of thinking we're going to use a lot going forward into calculus. You'll get used to it. It's not quite as bad as it seems, but the first time through, it must seem like just a gibberish that I'm throwing at you there. The idea being is I've wrote the function in a new form that I can look at and analyze and say for large x values, what's going to happen? For large x values, the function 2x cubed minus x squared plus 3 over x squared will look a lot like the graph of y equals 2x minus 1. That's all summarized in this paragraph here. For rational functions, linear oblique asymptotes happen when the degree of the numerator is exactly 1 more than the denominator. The equation of this linear oblique asymptote can be found by dividing the numerator by the denominator, which is what I did there. And I got y equals 2x minus 1. It says, be prepared though, the division may not always be so easy. May not always be. Well, it almost will always not be that easy. I made a really easy one to try and explain what was happening, but fortunately we have synthetic or long division to help. What I mean by that is I'll make up a really scary one. Y equals 2x to the power 4 minus 3x cubed plus 5x plus 1 divided by x cubed plus 3x squared minus 4x plus 7. Really, really scary looking. But to find the linear oblique asymptote, how do I know it's going to be a linear oblique? Degree 4, degree 3. It's exactly 1 more. How do I get the equation of the linear oblique asymptote? I can't do what I did in the last one. I need long division. That's why we need a long division. Sometimes you can use synthetic if the denominator is of degree 1. But in this case, it's way too complicated for that, and it looks really scary. Notice I had to put that plus 0x squared in there. But watch what happens. I take this thing and I go, okay, long division. I need a 2x in there. So that's 2x to the power 4 plus 6x cubed minus 8x squared plus 14x. Just make sure I did all those right. 2x to the 4, 6x cubed minus 8x squared plus 14x. Yes, subtract them all and I get negative 9x cubed plus 8x squared minus 9x plus 1. I brought down that plus 1. Just make sure I did that subtraction right. Negative 9, positive 8, 5 minus 14 is negative 9, yes. Next, I need a minus 9. So I get minus 9x cubed minus 27x squared plus 36x minus 63. Let's make sure I did all those right. Negative 9x cubed, negative 27x squared plus 36x, yes, minus 63. Subtract those, and what I get is 35x squared minus 45x plus 64. Let's just make sure I did that right. 8 minus negative 27 is 35, yes. Negative 9 minus 36, negative 45. 1 minus negative 3 is 64. Okay. Here's the big moment here, though. What I found out was this y, this function when I did long division, is made up of two parts. The quotient, 2x minus 9, plus a remainder, 35x squared minus 45x plus 64 over the divisor. And we didn't write a lot of them like that last chapter. We just acknowledged that it could be written like that. But watch what happens here. For x goes to infinity, y equals approximately 2x minus 9. Why? Because the degree here of the denominator was 3, the degree of the numerator was 2, and for large x values, that's going to go to 0. That's not going to be a big part. And so my equation of my oblique asymptote is y equals 2x minus 9. And that was the biggest, scariest example I can think of. But you can get the oblique just by doing your long division, and what you get up here, the quotient, will be the equation of your oblique asymptote. Very, very high level stuff. Except that it's just long division. I mean, it's very high level in understanding every little nuance of that example, but the facts are the situation isn't all that complicated as far as what math you have to do. Just divide them. You can make up study notes. It says define oblique asymptote. Degree of the top has to be higher by 1. Do long division. The answer you get is the oblique asymptote. That's simple from a math standpoint. To fully understand it, there's a lot to it there. Well, 2 examples. Here's where we're going to tie it all together. I now believe I've taught you enough that we can take a crazy example and graph it. I've left lots of space here. The 2 things we want to graph, we're going to try this one. 2x cubed minus x squared plus 3. Oops. Y equals 2x cubed. Already forgotten. Minus x squared plus 3. Over x squared. And what I'm going to try and do is take everything I've learned today to try and come up with a decent graph of this thing. Lots to talk about. Way back to domain issues. Domain issues was the first thing we talked about in this lesson. Domain issues. We can't have x squared come out to 0, so I've got a domain issue. X can't equal 0. You can handle this any way you want. Me personally, it helps my thought process. As soon as I have some information, I go down and put it on my graph, and I put my graph way down here. I'm going to try out, let me see how gray shows up here, or dark gray shows up here, because I don't want all these things to overtake my graph. I hope you can see that pretty good. Vertical asymptote. And if you're like, I thought you said they didn't have to be vertical asymptotes. Yeah, I'll deal with that in a second. For now, we're going to assume they're vertical asymptotes. We'll deal with the rest later. I like getting that on my graph, so I have some inkling as to what this is going to look like right off the hop. The next thing we learned was x-intercepts. And for x-intercepts, we set y equal to 0. And again, you can skip this step here because that denominator is always going to come over and multiply by the, 0. And when it multiplies by that, you're just going to get the 0. So as you get better at these, you may find that you want to skip that step and just go 0 equals the numerator when you're finding x-intercepts. Now this thing. Solving for when this is equal to 0. I got to factor this thing, so I got to go let p at x equal 2x cubed minus x squared plus 3. And I go p at 1. Equals, type that in my calculator. I get 4. P at negative 1. Ooh, 0. Therefore, x plus 1 is a factor. And so I have 0 equals, better do that, synthetic division. Okay, so k equals negative 1, 2x cubed minus 1x squared, 0x, and 3. 2, negative 2, add those together, negative 3. 3, add those together is 3, negative 3, 0. So I go, therefore, 0 equals, I found this first factor of x plus 1. Very unhappy with how neatly I wrote that, x plus 1, and the second factor, 2x squared minus 3x plus 3. Oh, that doesn't factor. Okay, so therefore x equals negative 1, or x equals negative b plus or minus square root of b squared minus 4ac. Let's nip this quadratic formula calculator stuff right in the bud right here. I want to see this substitution. I don't want to see how you made your calculator do it. If you're good enough to type that whole thing in your calculator, great. But what we get here is 9 minus 24, negative 15 over 4, and I get no more x-intercepts. So I just have the one x-intercept of x equals negative 1. Right there on my graph. I'm going to do my graph in purple. It doesn't seem like I have a lot of information. It really seems like, well, that's not nearly enough information to draw this graph. And you're right. That was just the x-intercepts. Now I'm going to go y-intercepts. Instead, I'm going to stop right there. And if you're thinking as I go through this procedure, if you're thinking, really? Really? I got to go through all these steps? And the answer is a giant yes. Absolutely. This is what it takes to analyze a function of this level. This is why these things are so difficult. There's so few people that know this math to know what it takes to really analyze these situations. That's what we're learning here, is this incredible analysis powers that this is going to give you. Y-intercept, set x equal to 0. I've lost my function. Oh, there it is. I get a 3 on the top and a 0 on the bottom. Y equals 3 over 0. What's happening? 3 divided by 0. Oh, in my calculator, 3 divided by 0. Error. No y-intercepts? Well, of course not. Vertical asymptote right along the y-axis. Maybe I should have seen that coming. No y-intercept. Very good. No y-intercept. Okay, and our new tools. Okay, let's take a look at this thing. We did this thing already. We found out it doesn't have a horizontal asymptote because the degree on the top was higher. But we did find out there was an oblique asymptote. We did the work on this above. There's an oblique asymptote. I did that division above. What did I get here? Oblique asymptote. Where was it? Where was it? Y equals 2x minus 1, way up there. Did that work and find out y equals 2x minus 1 is an oblique asymptote. Now, let me just take a minute to get that on here because it's important that we have this exactly right. So I'm going to get back to my using these lines here. Insert shapes, straight line. Ooh, it's all the way up there. No good. No, let's get rid of that. And let's certainly get rid of that. And down here. There, now we're where we want to go. Goodbye. Now when I insert the shape, I think it's going to be closer to where I want it to be. There it is. Much better. Okay, so y equals 2x minus 1. Let's see. You'll have a much easier time of doing this when you're not using crazy iPad Word to do it, but it's got to go through negative 1. And it's got to go up by 2s. So when it goes through negative 1, it's also got to go through there. Ooh, I think I got lucky and got it right on there. Negative 1 and going up by 2s. Yeah, there it is, oblique asymptote. And it's nice that it's in this light blue color. When you draw these things on there, you're going to want them on very light blue. And that's just what this function has to approach. Now you get all that way and you're like, yo, I don't think you've got enough information to graph this thing. And this is where your analysis skills come in. I want to talk about the section on the left-hand side of the vertical asymptote, the negative x values. I've got two asymptotes what this function has to head towards. So I'm going to put my pen right here at negative 1. and I know it has to approach that asymptote. Can it go this way, downwards? Yes, it could. But then how is it going to approach this oblique over here? There's only one way it can do this. It's got to go like this and approach the asymptote that way, and then approach this asymptote this way. If it went the other way, down to the right, it wouldn't approach the oblique on the left. Now, on the right-hand side, I argue we can think this out. I'm going to give you another weapon in the next example. Okay, so if you don't buy this thinking I'm about to do here, no problem. I'm going to give you another example, and the next example will really help you. In this one, I know on the right-hand side here, it can't possibly approach the asymptote on the negative side. If it did, it would be coming from here through there and approach the oblique. I know that can't be the case because I would get another x-intercept. And I found out there was no more x-intercepts. That is not going to work. So it's got to approach this vertical asymptote from here, not get down to an x-intercept, and then approach this oblique there. If you buy that thinking, great, you're done. Great job, you've done the whole graph. Wonderful. If you don't buy that thinking, I'm going to be able to do the analysis of where this is positive and negative, and I'll show you how to do that in the next example. So that's the graph of y equals 2x cubed. Let me just label that on there. This is the graph of y equals 2x cubed. I've already forgotten. Minus x squared plus 3. That last part that I pieced together there was all based on knowing that it had to approach the asymptotes and what was possible here. If that's a little confusing how I put all those pieces together, don't worry, I got one more weapon up my sleeve. It's not new. It's a weapon I showed you before in the previous chapter, but now we're going to put it to new use with a really good example. So if you're like, I sort of get what you did there, that's okay. Got one more big example to go. I'm going to make this into 2 videos, so there's a part 2 to this video coming right up after this. I just don't want the videos to get so incredibly large that there's any kind of problems, and I think that's about the limit there. So this video is going to end there, and then check out